Hey there, curious minds. Welcome back to Scientific Discovery Hub, your go-to channel for unraveling the universe's most mind-bending mysteries. Today, we're diving into a cosmic riddle that's got scientists scratching their heads. Is 3I Atlas a tiny icy snowball or a colossal interstellar iceberg? Picture this. Ampere's visitor from another star system zips through our solar system at 58 kilometers per second. Fast enough to escape the sun's gravity. That's 3I Atlas, the third confirmed interstellar comet ever discovered. But here's the twist. Its true size remains a hotly debated enigma. Early estimates suggested it might be a giant, but recent observations from the Hubble Space Telescope hint at a nucleus smaller than 1 kilometer. How can one object spark such confusion? The answer lies in its glowing coma, a veil of gas and dust that hides its icy core, creating a cosmic illusion that taunts astronomers. Why does this matter? Well, 3I Atlas isn't just another space rock. Its size could rewrite our understanding of how comets form, survive interstellar journeys, and even seed life across galaxies. Packed with CO2, cyanide, and hints of ancient origins, this comet might carry secrets from the Milky Way's earliest days. Could it be a relic older than our solar system? And what does its bizarre hyperbolic escape trajectory reveal about its journey through the galaxy? In this video, we'll unpack the science behind the debate, from the fiery dance of cometary activity to the cutting-edge techniques scientists use to pierce through the coma's haze. We'll compare 3I Atlas to its famous interstellar cousins, Oumuamua and Borisov, explore its potential to rewrite textbooks, and even touch on the controversial question, is it natural or something else? So buckle up. Whether you're a space enthusiast or new to astrophysics, this journey through comas, cosmic highways, and celestial detective work promises to blow your mind. Hit that subscribe button to join us as we decode the universe, one mystery at a time. Let's get started. In the vast, dark tapestry of the cosmos, where stars burn like distant lanterns and galaxies swirl in silent dance, a single object arrived unannounced. On 1 July 2025, the asteroid terrestrial impact last alert system, Atlas, in Chile, captured a fleeting glimpse of a traveler from the interstellar abyss, designated 3I Atlas. This comet hurtled through the solar system at 58 kilometers per second, a velocity so blistering that it defied the sun's gravitational pull. Unlike the icy wanderers born in the Kuiper Belt or Oort cloud, 3I Atlas hailed from beyond our stellar neighborhood. Its arrival was not a mere curiosity, but a profound riddle, a frozen relic from another star system, carrying secrets of a cosmos we barely comprehend. As scientists peered deeper into its mysteries, 3I Atlas proved elusive. Its nucleus, shrouded in a luminous coma of gas and dust, blurred the boundaries between truth and speculation. Was it a modest snowball, no wider than a mountain, or a colossal interstellar iceberg, its true scale hidden by the veil of its own activity? The answer mattered not just for cataloging comets, but for unraveling the origins of life, the architecture of distant worlds, and the ancient history of the Milky Way. The discovery of 3I Atlas began with a flicker in the night sky. On that fateful evening in Chile, the Atlas telescope detected an object moving with an uncanny speed. At 4.5 astronomical units, AU, from the sun, it was already racing inward at 61 kilometers per second, a velocity far exceeding the escape velocity of the solar system. Calculations revealed a hyperbolic trajectory, an orbit so extreme that it would never return. This was not a solar system object, but a transient guest from the galactic expanse. Hyperbolic trajectories are rare in nature. Most objects in the solar system follow elliptical paths, bound by the sun's gravity, but 3I Atlas's orbital eccentricity of 6.141, a number over 5 times that of the previous interstellar comet, 2I Borisov, marked it as something extraordinary. To achieve such a path, the comet must have originated from a region where the gravitational influence of stars is minimal. Tracing its journey backward, Astronomers determined that 3I Atlas approached the solar system from the direction of the galactic center, near the constellation Sagittarius. Yet its origin story remained incomplete. The comet's physical properties added to the mystery. Observations by the Hubble Space Telescope revealed a coma spanning thousands of kilometers, but the nucleus itself eluded direct measurement. The best estimates placed its diameter between 0.32 and 5.6 kilometers, though the true value likely lay at the lower end. The coma, a cloud of gas and dust, acted as a deceptive shroud, scattering light and distorting the nucleus's apparent size. Meanwhile, spectroscopic data from the James Webb Space Telescope unveiled a startling composition: an abundance of carbon dioxide, with traces of water ice, carbon monoxide, and carbonyl sulfide. Such a mix was unlike any solar system comet, hinting at a formation site far from the warmth of its parent star. Yet the most astonishing revelation was its age. By analyzing the comet's velocity relative to the Milky Way's disk, researchers concluded that 3I Atlas could be as old as 7 billion years, older than the solar system itself. If true, it belonged to the thick disk, a population of ancient stars and debris that predates the galaxy's spiral arms. This raised a haunting possibility. 3I Atlas might be a relic from the Milky Way's infancy, a survivor of a long-lost epoch. The study of 3I Atlas transcends planetary science. Its existence challenges fundamental assumptions about the distribution of matter in the galaxy. For decades, astronomers theorized that interstellar objects would be rare, ejected from young planetary systems by gravitational interactions. Yet 3I Atlas's ancient age and unique composition suggest otherwise. If comets like it formed in the thick disk, they could be remnants of the galaxy's earliest building blocks, primordial ice and rock forged in the chaos of star formation. Moreover, 3I Atlas's chemical makeup offers a window into alien protoplanetary disks. The dominance of carbon dioxide over water ice implies a formation environment colder and farther from its parent star than the CO2 frostline in our solar system. This challenges models of comet formation, which often assume that volatile compounds like CO2 are rare in the outer reaches of planetary systems. Did 3I Atlas originate in a system where such conditions were common? Or does its chemistry reflect a process unseen in our own backyard? The comet's age also raises philosophical questions. If 3I Atlas is 7 billion years old, it predates the formation of the solar system by 2.4 billion years. Could it have carried organic molecules, perhaps even the seeds of life, to its current trajectory? While no evidence of biological material has been found, the idea that interstellar objects might act as cosmic couriers of chemistry is no longer speculative. Every molecule released from 3I Atlas's nucleus is a clue to the universality of life's precursors. Even more provocative is the debate over its size. Early estimates suggesting a nucleus of 10-20 kilometers, far larger than typical comets, sparked controversy. Critics argued that the coma's brightness skewed measurements, but the discovery of high CO2 emissions supported the notion of a compact, active nucleus. Resolving this paradox could refine techniques for studying distant objects, improving our ability to detect interstellar visitors in the future. As 3I Atlas hurtled toward perihelion, its trajectory brought it within 1.36 AU of the Sun, closer than Earth or Mars. Observatories across the globe turned their gaze skyward, eager to witness its transformation. The James Webb Space Telescope would soon analyze its gas emissions, while the Hubble would track its evolution as it escaped the solar system. Yet 3I Atlas was not alone in its interstellar odyssey. Before it, 1I Oumuamua and 2I Borisov had traversed the void, each leaving behind a trail of unanswered questions. To understand 3I Atlas fully, we must situate it within the broader context of interstellar objects. How do these travelers differ from one another? What do their origins reveal about the diversity of planetary systems? And how might future discoveries reshape our cosmic perspective? In the next segment, we will journey beyond 3I Atlas to explore the legacy of interstellar visitors and the possibilities they unveil for humanity's place in the universe. This narrative weaves scientific precision with poetic reflection, inviting readers to ponder the profound implications of 3I Atlas's journey. Each paragraph builds upon the last, transitioning seamlessly from discovery to interpretation, from physics to philosophy, and from the microscopic to the cosmic. The structure ensures clarity while maintaining a contemplative tone, mirroring the awe inspired by this interstellar enigma. In the vast, silent expanse of interstellar space, where stars burn like distant lanterns, and the fabric of space-time stretches infinitely, a solitary traveler glides through the void. This is 3I Atlas, an interstellar comet born in the cradle of another star system, now wandering our cosmic neighborhood. Discovered in July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, in Chile, this celestial wanderer has captured the imagination of astronomers and stargazers alike as the third confirmed interstellar object to pass through the solar system, following the enigmatic 1I Oumuamua 2017 and the more comet-like 2I Borisov 2019. 3I Atlas represents a rare glimpse into the mysteries of the Milky Way. Its arrival is not merely an astronomical event, but a profound reminder of the universe's interconnectedness, a whisper across the cosmos from a time when our own solar system was young. 3I Atlas's journey began eons ago, perhaps in the dense, ancient heart of the Milky Way's thick disk, a region where stars older than the solar system itself reside. If its origin traces back to this stellar graveyard, the comet could be 7 billion years old. Older than Earth, older than the dinosaurs, older than the formation of the planets themselves. Yet despite its venerable age, 3I Atlas remains vibrant, its nucleus a frozen relic of primordial chaos, encased in a coma of gas and dust that dances under the sun's gaze. Its hyperbolic trajectory, a path too swift to be bound by the sun's gravity, reveals its true nature, an interloper from beyond, unmoored by the laws that govern our cosmic backyard. As it hurtles toward perihelion on 29 October 2025, 3I Atlas will come no closer than 1.8 AU from Earth, safe from any threat to our world, but tantalizingly close enough for telescopes to unravel its secrets. The Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories have already begun their vigil, peering into the comet's heart to decipher its composition. What they find: carbon dioxide-rich gas, water ice, and traces of cyanide and nickel paints a picture of a body forged in a different stellar nursery, one where the chemistry of life's building blocks may have taken root long before our own solar system came to be. This is more than a comet's passage. It is a voyage through time, a collision of epochs that invites us to ponder our place in the cosmos. How many such travelers have slipped through the solar system unnoticed? How often do fragments of other worlds visit us, bearing clues to the birth and death of stars? 3I Atlas does not simply cross our sky. It bridges the gap between the familiar and the unknown, a fleeting ambassador from the depths of the universe. And as we watch it fade into the darkness beyond the sun, we are left with a sense of awe, a quiet wonder at the infinite stories etched into the stars. The journey of 3I Atlas to our solar system is a tale of cosmic dynamics, governed by the invisible threads of gravity and the sheer velocity of its flight. To understand how this interstellar comet arrived at our doorstep, we must first grasp the forces that set it free from its home system. Like all interstellar objects, 3I Atlas did not simply drift aimlessly through space. Its trajectory was sculpted by the gravitational ballet of its native star system. Imagine a young planetary system, where gas giants and icy bodies orbit a fledgling star. Over millions of years, gravitational interactions between these bodies, perhaps a close encounter between a comet and a massive planet, could have imparted a sudden burst of kinetic energy. This slingshot effect, akin to a cosmic game of pinball, could have hurled 3I Atlas from its cradle into the interstellar void. Once ejected, 3I Atlas became a solitary wanderer, adrift in the vastness of the Milky Way. Its speed, 58 kilometers per second, relative to the Sun, is far beyond the escape velocity of our solar system, a velocity so great that no ordinary solar system object could achieve it. This hyperbolic excess velocity is the smoking gun of its interstellar origin. Unlike comets and asteroids that originate from the Oort cloud or the Kuiper belt, 3I Atlas is not bound by the sun's gravity. Instead, it follows a trajectory that curves sharply around the sun, a path so steep that it will eventually carry the comet back into the interstellar abyss, never to return. Detecting such a visitor is no small feat. The Milky Way is teeming with stars, their light a tapestry of brilliance against the dark. Against this backdrop, a faint, moving speck like 3I Atlas is nearly invisible. It was only through the relentless scanning of the Atlas survey, a network of automated telescopes designed to spot potential Earth-threatening objects, that the comet's approach was noticed. Atlas's twin telescopes in Hawaii and Chile, with their wide fields of view and rapid cadence, proved crucial in capturing the comet's first light. Yet even with this advanced technology, 3I Atlas remained elusive. Its path brought it dangerously close to the galactic center, a region choked with stars and interstellar dust, where the faint glow of a comet could easily be lost. It was only when follow-up observations by the Zwicky Transient Facility and the Vera C. Rubin Observatory confirmed its hyperbolic orbit that its true nature was revealed. The discovery of 3I Atlas underscores the power of modern astronomy to peer into the unseen corners of the universe. Surveys like Atlas, the Pan-STARRS project, and the Future Legacy Survey of Space and Time, LSST, are not merely tools for planetary defense. They are sentinels of the cosmos, capable of detecting the faintest whispers of interstellar visitors. With each new observation, these instruments refine our understanding of the solar system's place in the galaxy. They remind us that we are not alone in the void, that the stars are not static monuments but active participants in the grand cosmic drama. Yet, even with all our technological prowess, 3I Atlas remains an enigma. Its orbit, traced backward through time, points to the southern celestial hemisphere, a region where interstellar objects were once thought to be rare. This anomaly challenges our assumptions about the distribution of such travelers, hinting at a deeper complexity in the Milky Way's architecture. Perhaps the thick disk, a relic of the galaxy's violent youth, harbors countless comets like 3I Atlas, waiting to be discovered. Or perhaps 3I Atlas is a singular marvel, a cosmic oddity that defies expectation. Either way, its arrival compels us to rethink the boundaries of our knowledge, to consider that the universe is far more dynamic and interconnected than we dare imagine. The study of 3I Atlas is more than an exercise in observational astronomy. It is a journey into the origins of planetary systems and the chemical diversity of the Milky Way. Every grain of dust in its coma, every molecule of gas released into the vacuum of space, carries a story written in the crucible of another star. Through the lens of the James Webb Space Telescope, scientists have glimpsed a composition unlike any seen in the solar system. The comet's coma is rich in carbon dioxide, a gas far more abundant than in typical comets, suggesting that it formed in a region where temperatures were cold enough for CO2 to condense into ice. This implies that 3I Atlas's parent star system may have harbored a frostline, the boundary where volatile compounds freeze, that extended farther from the star than in our own solar system. Such a finding challenges existing models of planetary formation, hinting at the possibility of diverse architectures among extrasolar systems. Beyond its chemical makeup, 3I Atlas's age offers a tantalizing glimpse into the galactic past. If the comet indeed hails from the Milky Way's thick disk, a population of stars billions of years older than the Sun, it may have formed in an era when the galaxy was still in its infancy. The thick disk, a relic of the Milky Way's violent mergers and accretions, is a repository of ancient stellar populations, their light a testament to the galaxy's turbulent history. Amper's 7-billion-year-old comet is not merely a visitor from another system, it is a fossil from the dawn of the Milky Way, a relic of a time when stars and planets were born in a vastly different cosmic environment. Studying 3I Atlas's composition and structure could therefore provide critical insights into the conditions that shaped the earliest generations of planetary systems. The implications of such research extend far beyond the comet itself. Comets are often considered cosmic snowballs, fragile, icy bodies that preserve the pristine materials from which planets are born. If 3I Atlas shares this property, its organic molecules and volatile compounds may hold clues to the origins of life's building blocks in the universe. Carbon-based molecules, water ice, and complex organics have been detected in solar system comets, leading some to speculate that these icy wanderers may have seeded Earth with the ingredients necessary for life. Could 3I Atlas, with its alien chemistry, offer a parallel pathway? Its detection of cyanide and nickel, elements associated with prebiotic chemistry, raises intriguing questions about the universality of life's precursors. If such molecules are common in interstellar comets, the seeds of life may be scattered throughout the galaxy, carried on the winds of cosmic ejections. Yet 3I Atlas also presents challenges to our understanding of cometary behavior. Unlike solar system comets, which typically exhibit strong water-driven activity, 3I Atlas's coma is dominated by carbon dioxide. This suggests that its internal structure and thermal evolution differ significantly from those of local comets. The comet's relatively low mass, inferred from its dust ejection rates and nucleus size, further complicates its classification. Is 3I Atlas a typical interstellar comet, or does it represent a rare subclass of these objects? Answering these questions requires a multidisciplinary approach, combining spectroscopic data from ground-based telescopes, infrared observations from the James Webb Space Telescope, and models of cometary evolution. Perhaps most striking is the comet's trajectory, which aligns closely with the ecliptic, the plane of the solar system's planets. This alignment is statistically improbable, raising questions about the mechanisms that govern the orbits of interstellar objects. Are such alignments random, or do they hint at a hidden structure in the Milky Way's interstellar medium? The fact that 3I Atlas approached from the southern celestial hemisphere, a region where interstellar objects were previously thought to be scarce, further deepens the mystery. These anomalies challenge our assumptions about the distribution and frequency of interstellar visitors, suggesting that our solar system may be traversed by more of these objects than we realize. As 3I Atlas continues its journey through the inner solar system, each observation brings us closer to understanding not only the comet itself, but the broader context of its existence. Its passage is a reminder that the universe is a tapestry of interconnected histories, where the remnants of long-dead stars and forgotten planetary systems drift silently through the void. In the coming months, as the comet fades from view, its legacy will endure in the data it leaves behind, a cosmic message in a bottle, waiting to be decoded by future generations. As 3I Atlas draws closer to the Sun, its transformation begins, a delicate interplay between heat and ice that defines the essence of a comet. The Sun, a searing beacon of nuclear fusion, casts its rays upon the comet's nucleus, igniting a process that has captivated astronomers for centuries. Sublimation, the direct transition of ice into gas, becomes the driving force behind the comet's activity. Frozen reservoirs of carbon dioxide, water, and carbon monoxide within the nucleus warm, expanding violently to release jets of vapor and dust. This eruption gives rise to the coma, a glowing envelope of gas and particulate matter that envelops the nucleus like a luminous halo. The coma, in turn, stretches into tails that extend millions of kilometers into space, sculpted by the solar wind and radiation pressure. What makes this process so remarkable is its duality. The Sun, a source of destruction, paradoxically enables creation. The energy that would melt the comet's fragile structure instead fuels its spectacle, transforming a dark, icy body into a radiant celestial phenomenon. For 3I Atlas, this metamorphosis is amplified by its composition. Unlike solar system comets, which are primarily driven by water sublimation, 3I Atlas's coma is dominated by carbon dioxide. This difference in volatiles alters the dynamics of its activity, producing a more diffuse coma and a distinct spectral signature. The James Webb Space Telescope has already detected CO2 emissions spanning hundreds of thousands of kilometers, a testament to the comet's unique chemistry. The Sun's influence extends beyond the physical. Each molecule released into the coma carries a fingerprint of the comet's origin, a chemical signature that tells the story of its birthplace. Water ice, water vapor, and carbon monoxide in 3I Atlas's coma suggest that it formed in a region where temperatures were low enough for these compounds to condense, yet high enough to prevent the accumulation of more volatile species like methane. The presence of cyanide and nickel adds another layer of intrigue, hinting at the presence of complex organic molecules and metallic elements. These substances, forged in the crucible of a distant star system, may hold the keys to understanding the chemical pathways that lead to life. Yet, for all its beauty, cometary activity is a precarious dance. The closer 3I Atlas approaches the Sun, the more volatile its behavior becomes. Sudden outbursts, where the comet's brightness surges as a result of explosive sublimation, are not uncommon. In the case of 2I Borisov, such an event led to the ejection of a visible jet of gas and dust. Will 3I Atlas follow a similar fate, or will it maintain a steady, predictable rhythm? The answer lies in the balance between the comet's internal structure and the external forces acting upon it. Amper's fragile crust of insulating material may shield its interior from rapid heating, while fractures and fissures could allow for more dramatic eruptions. Even as we marvel at the comet's activity, we are reminded of its impermanence. The Sun's relentless pull accelerates 3I Atlas toward perihelion, a moment of closest approach that will mark the peak of its activity. Beyond this point, the comet will retreat into the cold, its volatile reservoirs diminished, its dust hails fading into the void. Yet the data it leaves behind will endure, a record of its brief but brilliant encounter with our corner of the cosmos. In this way, 3I Atlas becomes more than a transient visitor. It becomes a bridge between worlds, a messenger of the universe's hidden truths. As we shift our gaze to the next chapter of this celestial saga, we are left with a profound question. What else might we learn from the interplay between comets and the Sun? The answers await in the laboratories of observatories and the minds of scientists, eager to decode the secrets written in the stars. The cosmos is a realm of silent alchemy, where the dance between light and matter transforms the mundane into the extraordinary. Consider 3I Atlas, a wanderer from the depths of interstellar space, now drawn inexorably toward the Sun. Its journey is not merely a passage through the solar system, but a metamorphosis, a slow awakening from the cold, ancient slumber of its birthplace. As it glides inward, the Sun's radiant touch ignites a transformation in its frozen heart, unraveling layers of ice and dust in a spectacle of cosmic artistry. Yet this process is not random chaos. It is governed by the immutable laws of physics, a delicate balance of heat, pressure, and molecular escape. To witness this phenomenon is to glimpse the life cycle of a comet, a fleeting yet profound interplay of energy and entropy. What does this tell us about 3I Atlas itself? How does its behavior compare to the comets of our own solar system? And what secrets might its activity reveal about its alien origins? At the core of every comet lies a nucleus, a chaotic mixture of ice, rock, and organic compounds, often no larger than a mountain. When a comet ventures too close to the Sun, the energy it receives is no mere whisper. It is a crescendo of thermal forces capable of melting entire worlds. For 3I Atlas, this process began long before its discovery, as early as 6.4 astronomical units AU from the Sun, where the ambient temperature is still frigid, but the solar wind carries enough energy to trigger sublimation. Volatile ices, primarily carbon dioxide, with traces of water and carbon monoxide, begin to transform directly from solid to gas, bypassing the liquid phase in a process known as sublimation. This release of gas is not uniform. It depends on the composition of the nucleus and the angle at which the Sun's rays strike its surface. The escaping gases carry with them dust particles, tiny grains of silicates and carbonaceous material that had been locked beneath the ice for eons. Together, they form a coma, a diffuse, glowing halo that can span tens of thousands of kilometers. The coma is not static. It shifts and evolves as the comet's surface is pummeled by solar radiation and charged particles. Within this cloud, complex chemical reactions occur, driven by the energy of the Sun. Molecules break apart and recombine, forming new compounds that may never exist in the colder reaches of space. Meanwhile, the solar wind, a stream of charged particles flowing from the Sun, interacts with the coma, stripping away electrons and creating ionized gas that forms a distinct glowing tail. This tail, often split into two, one composed of charged particles and another of dust, is a testament to the Sun's dominance over the comet's fate. For 3I Atlas, the Comet is particularly noteworthy. Observations by the James Webb Space Telescope, JWST, have revealed a carbon dioxide-rich envelope, far more abundant than in most comets of the solar system. This suggests that the nucleus of 3I Atlas is either exceptionally rich in CO2, or that its surface is insulated by a layer of more refractory materials, delaying the sublimation of water ice. The presence of cyanide gas and atomic nickel vapor adds another layer of complexity, hinting at a chemical history shaped by the unique conditions of its home system. Unlike the predictable patterns of cometary activity observed in solar system objects, 3I Atlas's behavior defies easy categorization, offering a glimpse into the diversity of cometary evolution beyond our own neighborhood. The activity of 3I Atlas is not merely a display of cosmic fireworks. It is a window into the comet's past and a challenge to existing models of cometary science. Most comets from the solar system, such as Halley's Comet or 67P, Churyumov-Gerasimenko, exhibit a gradual increase in activity as they approach the Sun, with water ice playing a dominant role in their outgassing. However, 3I Atlas's CO2-driven coma suggests a different evolutionary path. Carbon dioxide sublimates at much lower temperatures than water ice, meaning that 3I Atlas may have remained active at distances where solar system comets are still dormant. This raises intriguing questions about its origin. Could it have formed in a colder, more distant region of its parent star's protoplanetary disk, where CO2 frost lines extended farther out than in the early solar system? Or does its composition reflect a different chemical equilibrium in the star system from which it hails, one with less water and more carbon-based ices? Moreover, the comet's activity provides clues about its physical structure. The fact that its nucleus remains shrouded in a dense coma, making direct observation difficult, implies that it may be surrounded by a thick layer of dust and refractory materials. This insulation could explain why its CO2-rich gases are released so prominently, as the overlying material prevents water ice from sublimating until the comet is much closer to the Sun. Such a structure is not unheard of in comets. Some solar system objects, like the enigmatic C2016 R2 Pan-stars, also exhibit unusually high CO2 abundances. But the scale of 3I Atlas's activity sets it apart. The presence of cyanide and nickel vapor further complicates the picture, as these elements are typically associated with the breakdown of organic compounds under intense solar radiation. Their detection in the coma suggests that 3I Atlas's surface is undergoing rapid chemical changes, a process that could offer insights into the types of molecules that might exist in the atmospheres of exoplanets, or the building blocks of life in distant star systems. Perhaps most profoundly, 3I Atlas's activity underscores the dynamic nature of interstellar objects. Unlike 1I Oumuamua, which showed no signs of cometary activity and baffled scientists with its smooth, metallic-like appearance, or 2I Borisov, which behaved much like a typical solar system comet, 3I Atlas occupies a middle ground. Its behavior is neither entirely alien nor entirely familiar, bridging the gap between the strange and the known. This duality challenges the assumption that all interstellar objects must conform to a single archetype. Instead, it suggests a vast and varied population of interstellar comets, each shaped by the unique conditions of their home systems. Some may be rich in water and organic molecules, others dominated by CO2 and refractory dust, and still others may harbor entirely unknown chemical profiles. The study of 3I Atlas is thus not just an investigation into one object, but a step toward understanding the broader tapestry of interstellar material that drifts through the galaxy. Yet, for all its luminous drama, the coma of 3I Atlas is but a fleeting moment in its eternal journey. The true story of its passage through the solar system is written not in the glow of its dust, but in the trajectory it follows, a hyperbolic path that will carry it back into the void, forever unbound by the Sun's gravity. This trajectory is more than a mathematical abstraction. It is a cosmic signature, a record of the forces that shaped 3I Atlas's journey and the mysteries of its origin. To understand this path is to trace the comet's steps from the depths of interstellar space to its brief encounter with the solar system, and to glimpse the unseen hands that may have nudged it along the way. In the next segment, we will delve into the physics of hyperbolic orbits, exploring how 3I Atlas's velocity and direction reveal the secrets of its interstellar voyage. In the vast, silent expanse of the cosmos, where time stretches into epochs and distances dwarf human comprehension, the solar system is a fleeting oasis, a fragile cradle of life adrift in the galactic sea. Yet even here, in this familiar domain, the universe reminds us of its boundless curiosity. Among the countless celestial wanderers that have traversed the heavens, one stands apart: 3I Atlas, a comet born not of our solar system, but of another stellar home, millions of light years away. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas in Chile. This interstellar traveler carries with it the whispers of ancient stars and the secrets of a distant past. 3I Atlas is the third confirmed interstellar object to grace our cosmic neighborhood, following the enigmatic 1I Oumuamua in 2017 and the more recent 2I Borisov in 2019. Yet, its story is unique. Unlike its predecessors, 3I Atlas arrives not as a silent, mysterious rock, but as an active comet, its icy heart warmed by the sun into a luminous spectacle of gas and dust. Its trajectory, a hyperbolic arc that defies the gravitational pull of the solar system, is a testament to its origins beyond our star's dominion. As it hurtles through the inner solar system at 58 kilometers per second, 3I Atlas offers a rare opportunity to glimpse the chemistry and dynamics of a world that formed in the shadow of a foreign star. This comet is not merely a visitor. It is a messenger. Its arrival stirs questions about the nature of our galaxy, the prevalence of interstellar wanderers, and the possibility that such objects might carry the building blocks of life, or even more profound mysteries across the void. To understand 3I Atlas is to peer into the depths of the Milky Way's history, to trace the threads of cosmic evolution that bind stars, planets, and perhaps even life itself. To comprehend 3I Atlas's journey, we must first unravel the physics that govern its path. Most objects in the solar system, planets, moons, asteroids, are ensnared in the sun's gravitational embrace, following elliptical orbits that loop perpetually around our star. These orbits, defined by Kepler's laws, are stable and predictable, a dance choreographed by gravity alone. But 3I Atlas is different. Its trajectory is a hyperbola, a near straight line that curves just enough to escape the sun's grasp entirely. The key to this escape lies in velocity. For an object to break free from the sun's gravity, it must exceed the escape velocity, the minimum speed required to overcome the gravitational pull. At the distance of Earth's orbit, this velocity is approximately 42.1 kilometers per second. 3I Atlas arrives at the solar system with a hyperbolic excess velocity of 58 kilometers per second, far surpassing this threshold. This speed is not accidental. It is the product of a complex interplay between the comet's origin and the gravitational forces of its parent star system. Orbital eccentricity quantifies the shape of an orbit. Elliptical orbits have eccentricities less than 1,000, while hyperbolic orbits exceed this value. 3I Atlas's eccentricity of 6.14 is staggering, making it the most hyperbolic interstellar object yet observed. For comparison, 1I Oumuamua had an eccentricity of 1.2, and 2I Borisov's was 3.4. Such a high eccentricity means 3I Atlas's path is almost linear, a cosmic arrow fired from the depths of interstellar space. What drives this velocity? The answer lies in the comet's origin. Tracing 3I Atlas's trajectory backward reveals it entered the solar system from the direction of the constellation Sagittarius, near the Milky Way's galactic center. Its motion is not random. It carries a signature of the galaxy itself. The comet's velocity can be decomposed into three components: radial Lausch, transverse volts, and vertical Lau watts. 3I Atlas's U component of minus 51.0 kilometers per second indicates it is moving away from the galactic center, while its watts component of 18.5 kilometers per second shows it is ascending above the galactic plane. Together, these velocities suggest it hails from the Milky Way's thick disk, a population of older stars with lower metallicities than the Sun. The thick disk is a relic of the galaxy's early history, a reservoir of stars and debris dating back billions of years. If 3I Atlas indeed originates from this region, it could be older than the solar system itself, a remnant of a time when the Milky Way was young and chaotic. This possibility raises profound questions. Could 3I Atlas have formed in a protoplanetary disk around a long-dead star? Did it once orbit a planet, only to be ejected by gravitational forces? The answers lie in the comet's composition and the clues hidden within its coma. As 3I Atlas approaches the Sun, its icy nucleus awakens. The heat of our star sublimates frozen volatiles, carbon dioxide, water, and carbon monoxide, into gas, which in turn lifts dust from the comet's surface. This process creates a coma, a glowing halo of gas and particles that expands outward, and a tail that streams away from the Sun. Observations by the Hubble Space Telescope and the James Webb Space Telescope, JWST, reveal a coma spanning thousands of kilometers, rich in carbon dioxide and water ice. These findings are critical. The high CO2 to water ratio, among the highest ever recorded in a comet, suggests 3I Atlas formed far from its parent star, beyond the CO2 frost line, where temperatures are frigid enough for carbon dioxide to condense into ice. The presence of water ice and vapor adds another layer of intrigue. While water is common in solar system comets, its distribution in interstellar ones is less understood. JWST's spectroscopic data indicate that the water ice in 3I Atlas's coma consists of fine, submicrometer grains, likely ejected by the sublimation of CO2 and CO. This implies a dynamic interaction between the comet's volatile ices, a process that may mirror the chemistry of primordial planetary systems. Furthermore, the detection of cyanide gas and atomic nickel vapor by the Very Large Telescope VLT underscores the comet's complexity. These molecules, commonly found in comets, hint at the presence of organic compounds and metals, ingredients that could play a role in the emergence of life. Yet, 3I Atlas is not just a repository of exotic chemistry. Its trajectory, a retrograde path, tilted 175 degrees from the ecliptic, challenges assumptions about the origins of interstellar objects. Most models predict that such objects would arrive from the direction of the solar system's apex, the point in the sky toward which the Sun is moving through the galaxy. 3I Atlas's southern origin, however, is an anomaly. This discrepancy suggests either a gap in our understanding of galactic dynamics, or the possibility that interstellar objects from the southern hemisphere are more common than previously thought. The comet's age further deepens the mystery. If 3I Atlas belongs to the thick disk, it could be 7 to 14 billion years old, predating the solar system by nearly 3 billion years. Such an object would have witnessed the galaxy's violent youth, when star formation was rampant and supernovae sculpted the cosmic landscape. Its survival through eons is a testament to the resilience of interstellar debris. Yet, how did it endure? Simulations suggest that gravitational interactions with stars and molecular clouds may have altered its trajectory, gradually guiding it toward the solar system. Measuring the size of 3I Atlas's nucleus is a formidable task. Unlike stars or planets, comets are shrouded in their own comas, making direct observation of their solid cores difficult. The Hubble Space Telescope estimates the nucleus to be between 0.32 and 5.6 kilometers in diameter, though the true figure is likely at the lower end of this range. This uncertainty stems from the coma's brilliance, which outshines the nucleus and distorts its apparent size. Advanced instruments like JWST and the Very Large Telescope, VLT, are crucial in disentangling these signals, using spectroscopy and high-resolution imaging to probe the comet's innermost secrets. The next segment will delve into the technological and methodological innovations that allow scientists to pierce the veil of the coma, revealing the nucleus hidden within. From adaptive optics to space-based observatories, these tools are the keys to unlocking 3I Atlas's final riddles. As the comet continues its journey toward perihelion, Each observation brings us closer to understanding not just this singular visitor, but the vast interconnected web of the cosmos. This script balances scientific detail with poetic reflection, inviting readers to contemplate the universe through the lens of Three-Eye Atlas. Each section builds on the last, weaving a narrative that bridges discovery and wonder. In the vast silent expanse of the cosmos, where the boundaries of the known universe stretch into infinity, a new interloper has arrived. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas Telescope in Chile, Three-Eye Atlas, a comet born among the stars of another stellar system, has embarked on a brief but profound journey through our solar system. Its arrival marks a milestone in human exploration, for it is the third confirmed interstellar object to traverse this cosmic neighborhood, following the enigmatic One-Eye Oumuamua 2017 and the more recently identified Two-Eye Borisov 2019. Yet unlike its predecessors, Three-Eye Atlas carries with it a unique signature, a hyperbolic trajectory that propels it at a blistering 58 kilometers per second, a speed sufficient to escape the sun's gravitational grasp entirely. This comet is not merely a visitor, it is a relic of another world, a time capsule from the distant reaches of the Milky Way. Its nucleus, shrouded in a glowing coma of gas and dust, tells stories of the frigid, ancient environments where it was forged. As it glides through the inner solar system, Three-Eye Atlas invites us to ponder the shared history of stars and planets across galaxies, the dynamic dance of matter and energy that shapes existence itself. To observe this comet is to witness a fleeting moment of cosmic connection, a reminder that we are not alone in the universe, but part of a grand interconnected tapestry. Yet Three-Eye Atlas remains elusive. Its nucleus, the heart of the comet, is hidden beneath a veil of outgassed material, a swirling haze that obscures its true size and nature. This cosmic illusion challenges our understanding, forcing us to peer through layers of data and theory to unravel its mysteries. What can this interstellar wanderer teach us about the birthplaces of comets, the evolution of planetary systems, and the origins of life's building blocks? As humanity turns its gaze skyward, Three-Eye Atlas becomes a symbol of both humility and ambition, a reminder that the universe is vast and our knowledge is but a flicker in its endless night. The discovery of Three-Eye Atlas was a triumph of modern astronomy, a testament to the power of automated surveys and global collaboration. Initially spotted by the Atlas telescope in Chile, the object's peculiar motion immediately drew attention. Follow-up observations from observatories around the world, including the Zwicky Transient Facility and the Hubble Space Telescope, confirmed its interstellar origin. With an orbital eccentricity of 6.1414, the highest of any known interstellar object, Three-Eye Atlas's path is unmistakably unbound, a trajectory that traces back to the distant Milky Way. At the heart of this comet lies a paradox. Its nucleus is hidden, yet its activity is undeniable. As Three-Eye Atlas approaches the sun, solar radiation heats its icy core, triggering sublimation of volatile materials. Water, ice, carbon dioxide, and other compounds transform into gas, carrying dust into the coma, the comet's luminous envelope. The James Webb Space Telescope, JWST, has revealed that Three-Eye Atlas's coma is unusually rich in carbon dioxide, a composition distinct from most solar system comets. This anomaly hints at its origin beyond the frost lines of its parent star, where CO2 could condense into solid form. Meanwhile, the Very Large Telescope, THO-LT, has detected cyanide gas and atomic nickel vapor, elements that mirror the chemistry of comets in our own backyard. Such findings blur the line between the familiar and the alien, suggesting that the processes shaping planetary systems may be universal. Determining the size of Three-Eye Atlas's nucleus, however, remains a challenge. Early estimates from Hubble data placed it between 0.32 and 5.6 kilometers in diameter. Though the comet's coma complicates measurements, the nucleus appears fainter than the surrounding haze, its light diluted by the reflective dust. This ambiguity underscores the limitations of remote observation. To truly understand Three-Eye Atlas, We would need a spacecraft to sample its surface, yet launching such a mission is impossible with current technology. The comet's velocity demands a delta V of 24 kilometers per second, far beyond the capabilities of any rocket. Instead, telescopes like JWST and the newly operational Vera C. Rubin Observatory serve as our proxies, capturing fleeting glimpses of a world that will soon vanish into interstellar darkness. Even as 3I Atlas draws closer to the Sun, its behavior defies easy categorization. Its coma exhibits a reddish hue, a signature of organic compounds, and its dust tail stretches tens of thousands of kilometers. Yet the comet lacks the dramatic outbursts seen in others, its activity steady and methodical. This stability raises questions about its internal structure. Is its nucleus compact and resilient, or does it harbor a fragile, layered interior? The answers lie buried beneath the coma, waiting for the next breakthrough in observational technique. To trace 3I Atlas's origin is to journey backward in time. Its trajectory, plotted against the backdrop of the Milky Way, points to the galaxy's thick disk, a region populated by ancient stars, some of which are over 10 billion years old. If 3I Atlas hails from this domain, it could be a relic predating the solar system itself, a fragment of a protoplanetary disk that coalesced eons ago. Such a finding would rewrite our understanding of interstellar objects, revealing them not as rare anomalies, but as echoes of a shared galactic history. The comet's velocity vector adds another layer of intrigue. Unlike previous interstellar visitors, which approach from the direction of the solar apex, the point in the sky where the Sun moves relative to nearby stars, 3I Atlas arrives from the southern celestial hemisphere. This deviation challenges assumptions about the distribution of interstellar debris, suggesting that such objects may originate from diverse regions of the galaxy. Moreover, its vertical velocity component, 18.5 kilometers per second relative to the galactic plane, implies a tilted orbit, a path that could have carried it through the turbulent environments of stellar nurseries or dense molecular clouds. These encounters may have altered its trajectory, scattering it toward the solar system like a pebble kicked up by the tide. The chemical composition of 3I Atlas's coma further deepens the mystery. While its abundance of carbon dioxide suggests a formation site far from its parent star, the presence of water ice and organics mirrors the conditions of the outer solar system. Could this comet be a hybrid, a product of both extreme cold and dynamic chemical processes? Or does its chemistry reflect the unique history of its parent star, a system where ice and rock mingled in ways unfamiliar to our own? The answers lie in the ratios of isotopes and the distribution of volatile compounds, data that JWST and SphereX are beginning to collect. Yet 3I Atlas is not without controversy. In July 2025, Harvard astrophysicist Avi Loeb speculated that the comet might be an alien spacecraft, citing its trajectory, size, and chemical profile as anomalous. While the hypothesis captured public imagination, the scientific community swiftly rejected it. Observations confirmed cometary activity, with clear evidence of CO2, water, and cyanide emissions. The absence of detectable metals like iron, coupled with the lack of artificial structures, rendered the idea implausible. As astronomer Darrell Seligman noted, the evidence presented is not extraordinary, so the claim must be as well. This episode underscores the tension between curiosity and skepticism, a balance essential to scientific progress. Even as debates unfold, 3I Atlas continues its silent voyage. By October 2025, it will reach perihelion, its closest point to the Sun, before departing the solar system forever. Mars orbiters may capture final images, while Hubble and JWST will track its fading glow. These observations will refine our models of interstellar comets, offering insights into their formation, evolution, and prevalence. Perhaps future missions equipped with faster propulsion or advanced robotics will one day intercept such travelers, unlocking their secrets in person. Until then, 3I Atlas remains a fleeting beacon, a reminder that the universe is teeming with stories waiting to be told. As 3I Atlas hurtles toward its solar encounter, its coma swells with volatile compounds, each molecule a note in a cosmic symphony. The carbon dioxide, water, and organics streaming from its nucleus hint at a history shaped by the frigid void of interstellar space. Yet these ingredients are not random. They are the fingerprints of a process as old as the galaxy itself, a recipe for worlds, and perhaps for life. What other secrets lie hidden in this comet's chemistry? The next segment will delve into the intricate dance of molecules that defines 3I Atlas's essence, exploring how its composition connects to the origins of our solar system and the potential for life elsewhere in the cosmos. From the frost lines of distant stars to the laboratories of Earth, the story of 3I Atlas is a bridge between the known and the unknown, a journey that begins in the dark and ends in the light of understanding. In the vast expanse of the cosmos, every object tells a story, one written in the language of chemistry. Comets, in particular, are like frozen time capsules, preserving the primordial materials from which they were born. Among the countless comets that have graced the inner solar system, 3I Atlas stands out as a rare interstellar visitor, carrying a chemical signature unlike any other. Its coma, a swirling cloud of gas and dust, is a treasure trove of volatile compounds, carbon dioxide, water, cyanide, and even traces of atomic nickel. These ingredients are not random, they are the echoes of a distant stellar nursery, a recipe forged in the crucible of another star system. To understand 3I Atlas is to decipher a cosmic recipe, one that holds clues to its origins and the conditions under which it was created. The question remains, what does this chemical fingerprint reveal about the comet's birthplace, and how does it compare to the comets that hail from our own solar system? The most striking feature of 3I Atlas's chemical composition is its unusually high ratio of carbon dioxide to water. Observations by the James Webb Space Telescope, JWST, have shown that the mixing ratio of CO2 relative to water in the comet's coma is approximately 8.01, a figure that dwarfs the ratios seen in nearly all solar system comets. Typically, comets from our own planetary neighborhood exhibit CO2 to water ratios of less than 1:1, with water dominating the volatile inventory. The extreme abundance of carbon dioxide in 3I Atlas suggests that it formed in a region of its parent star system, where temperatures were cold enough for CO2 to freeze and accumulate in icy bodies. Such conditions occur beyond the CO2 frost line, a theoretical boundary in a protoplanetary disk where carbon dioxide can condense into solid form. In our solar system, this frost line lies far beyond the orbit of Neptune, in the frigid reaches of the Kuiper belt and the scattered disk. The fact that 3I Atlas possesses such a high CO2 content implies that it originated in a similarly remote and cold region of its home system, one where volatile ices could persist for eons without sublimating into gas. Yet CO2 is not the only ingredient in 3I Atlas's cosmic recipe. Alongside it are water ice, water vapor, carbon monoxide, and carbonyl sulfide, compounds commonly found in comets from the solar system. The presence of water ice in particular raises intriguing questions. Unlike CO2, which requires extremely low temperatures to freeze, water ice can form in a wider range of environments. The detection of water ice in 3I Atlas's coma, combined with the high CO2 content, suggests that the comet's parent star system had a unique chemical balance, possibly favoring the preservation of CO2 over water. This could mean that the protoplanetary disks surrounding 3I Atlas's parent star was either richer in CO2 or lacked the necessary conditions to allow water ice to dominate. Alternatively, the comet may have undergone a process of selective sublimation, where CO2 escaped more readily than water, leaving behind a higher concentration of CO2 in the coma. Perhaps the most surprising component of 3I Atlas's chemical profile is the presence of cyanide and atomic nickel. Cyanide, a molecule composed of a carbon atom triple bonded to a nitrogen atom, is a common constituent of cometary comas and has long been associated with the organic chemistry of the solar system. The detection of cyanide in 3I Atlas's coma is not unexpected. In fact, it mirrors the composition of solar system comets like Hale-Bopp and Halley. What is remarkable, however, is the simultaneous detection of atomic nickel vapor, a substance rarely observed in cometary emissions, Atomic nickel is typically found in the outgassing of comets, when certain organic compounds, such as nickel tetracarbonyl, decompose under the influence of solar radiation or space weathering. The fact that 3I Atlas emits nickel vapor at concentrations comparable to those seen in solar system comets suggests that its chemical evolution shares similarities with the comets of our own planetary neighborhood, despite its interstellar origin. However, not all expected molecular signatures are present in 3I Atlas. Notably absent are carbon chain compounds, such as C2 and C3, which are often found in the Comet of solar system comets. These molecules, composed of 2 or 3 linked carbon atoms, are typically produced when organic material is broken down by solar radiation or thermal processes. The lack of C2 and C3 in 3I Atlas's coma implies that the comet is either chemically distinct from solar system comets, or that its organic inventory has been altered by external factors, such as prolonged exposure to interstellar radiation. The absence of these carbon chain compounds also places 3I Atlas among the most carbon chain depleted comets ever observed, suggesting that its parent star system may have lacked the necessary conditions to form or preserve such complex organic structures. These chemical findings are not merely academic curiosities. They are vital clues to the comet's history and the environment in which it was born. The JWST's ability to detect and analyze these volatile compounds in unprecedented detail has provided astronomers with a window into the chemistry of an alien world. By studying 3I Atlas's chemical fingerprint, scientists can reconstruct the conditions that existed in its parent star system billions of years ago. Did it form in a disk similar to our own, or was its birthplace fundamentally different? The answers lie in the intricate dance of molecules within its coma, each one a whisper from the past. The chemical composition of 3I Atlas offers more than just insights into its own origins. It provides a glimpse into the broader diversity of comet formation across the galaxy. The high abundance of CO2 and the absence of carbon chain compounds suggest that the comet's parent star system may have followed a different evolutionary path than our own. Perhaps its protoplanetary disk was enriched in CO2 due to a unique combination of temperature, pressure, and chemical processes. Alternatively, the disk may have experienced intense radiation or stellar winds that stripped away organic material, leaving behind a CO2-dominated reservoir of volatile ices. Either explanation challenges the assumption that all star systems evolve in similar ways, reinforcing the idea that planetary formation is a highly variable and complex process. Moreover, the presence of atomic nickel in 3I Atlas's coma raises intriguing questions about the chemical interactions that occur in interstellar space. Nickel is typically found in the Earth's core and in meteorites, where it is bound to iron and other metals. Its detection in a comet's coma suggests that nickel-bearing compounds can be liberated through the breakdown of more complex molecules, a process that may be influenced by solar radiation or space weathering. The fact that 3I Atlas emits nickel at concentrations similar to those seen in solar system comets implies that the mechanisms responsible for releasing nickel into cometary emissions are not exclusive to our own planetary neighborhood. This could mean that the chemical processes shaping comets are universal, operating in a wide range of stellar environments. The implications of these findings extend beyond the study of individual comets. They speak to the fundamental question of whether the building blocks of life, carbon-based molecules, water, and other essential compounds are common throughout the galaxy, or uniquely tied to the conditions of our solar system. The detection of cyanide in 3I Atlas's coma is particularly relevant in this regard. Cyanide, though toxic in terrestrial biology, plays a critical role in prebiotic chemistry, serving as a precursor to amino acids and other organic molecules. The fact that a comet from another star system carries such a compound suggests that the raw materials for life may be widespread in the universe, carried by interstellar visitors like 3I Atlas. Furthermore, the study of 3I Atlas's chemical composition highlights the importance of comparative planetary science. By comparing the volatile inventories of interstellar comets with those of solar system comets, astronomers can identify patterns and anomalies that may reveal the underlying principles governing planetary formation. For instance, the high CO2 content of 3I Atlas contrasts sharply with the CO2-poor comets of our own solar system, raising the possibility that the chemical makeup of comets is strongly influenced by the specific conditions of their host star system. This, in turn, suggests that the diversity of planetary systems extends beyond architecture and orbital dynamics. It includes the chemical recipes that define their building blocks. As the comet continues its journey through the inner solar system, further observations will refine our understanding of its chemical composition. The JWST, with its unparalleled sensitivity to infrared wavelengths, will play a crucial role in detecting and quantifying the various molecular species in 3I Atlas's coma. Additionally, ultraviolet spectroscopy by the Hubble Space Telescope will provide insights into the comet's gas emissions and the distribution of sulfur and oxygen, elements that may shed light on its internal structure. With each new observation, the story of 3I Atlas becomes clearer, revealing a cosmic traveler that is both familiar and alien, a comet that carries the legacy of another star system while echoing the chemical heritage of our own. While the chemical composition of 3I Atlas offers a glimpse into its origins, another aspect of the comet's identity remains shrouded in mystery: its age. Unlike the comets of our own solar system, which have been shaped by billions of years of gravitational interactions and solar heating, 3I Atlas is a transient visitor, a relic from the depths of interstellar space. Yet how old is it? Could it be younger than our solar system, or has it wandered the cosmos for eons, untouched by the forces that govern the planets and asteroids of our planetary neighborhood? The answer lies not just in the comet's chemical makeup, but in the trajectory it has taken across the Milky Way and the gravitational forces that have shaped its journey. To unravel the age of 3I Atlas is to embark on a voyage through time itself, tracing the comet's path backward through the vast expanse of the galaxy to uncover the secrets of its ancient past. In the vast, silent expanse of the cosmos, where stars burn like distant lanterns and galaxies spiral in endless dance, a traveler emerged from the shadows, discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS. In Chile, 3I Atlas, also known as CEAS 2025 N1, ATLAS, is an interstellar comet, a wanderer born in another stellar cradle, and now traversing our solar system. This icy emissary, the third interstellar object confirmed to pass through our cosmic neighborhood, after 1I Oumuamua and 2I Borisov, carries secrets older than our own planetary family. At the moment of its discovery, 3I Atlas was already 4.5 AU from the Sun, a distance greater than the orbit of Jupiter, yet it was hurtling inward at an astonishing speed of 58 kilometers per second, a velocity far exceeding the gravitational pull of our star. Its trajectory, described by an orbital eccentricity of 6.14, a number so extreme that it appears almost linear, is a testament to its interstellar origins. Unlike the familiar comets of our solar system, which trace elliptical paths bound by the Sun's gravity, 3I Atlas is a transient visitor, destined to escape into the void after its brief encounter with our star. This comet is not merely a cosmic oddity, it is a bridge between worlds. Its arrival stirs questions about the nature of our galaxy, the birthplaces of celestial bodies, and the unseen forces that scatter fragments of distant systems across the interstellar medium. As it glides through the inner solar system, 3I Atlas invites us to gaze beyond the familiar, to ponder the infinite tapestry of the universe and our place within it. To understand 3I Atlas is to unravel the mysteries of its form and function. At its heart lies a nucleus, a frozen core of rock, ice and volatile compounds, surrounded by a coma, a tenuous envelope of gas and dust. This coma, illuminated by sunlight, gives the comet its ethereal glow. The Sun, that relentless fusion reactor at the center of our solar system, is the architect of 3I Atlas's activity. As the comet draws closer to our star, solar radiation warms its surface, causing volatile ices, primarily carbon dioxide, water and carbon monoxide, to sublimate into gas. This process, akin to a slow, silent eruption, propels dust particles into space, sculpting the coma and forming the comet's iconic tail. Observations by the Hubble Space Telescope have revealed that 3I Atlas's nucleus is likely less than 1 kilometer in diameter, a mere speck in the grand scale of the cosmos. Yet its coma stretches tens of thousands of kilometers, a ghostly halo of expelled material. The James Webb Space Telescope, JWST, has further unveiled the comet's chemical fingerprint, an unusually rich abundance of carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. This composition sets 3I Atlas apart from solar system comets, which typically exhibit higher ratios of water to CO2. Such anomalies hint at a different origin story, one shaped by the frigid depths of another star system. Even more intriguing is the detection of cyanide gas and atomic nickel vapor in its coma. These substances, uncommon in interstellar space, suggest complex chemical processes at play. The Very Large Telescope, VLT, has tracked the evolution of these emissions, revealing a gradual increase in concentration as the comet approaches the Sun. This dynamic transformation mirrors the behavior of solar system comets, yet 3I Atlas's chemistry remains enigmatic. Why does it emit such quantities of CO2? What processes govern its release of nickel and cyanide? These questions linger unanswered as the comet continues its lonely voyage. The origin of 3I Atlas is a puzzle etched into the fabric of the galaxy. By analyzing its hyperbolic trajectory and velocity components, astronomers have traced its path to the southern celestial hemisphere, near the galactic center, here in the crowded heart of the Milky Way. The thick disk, a population of ancient stars with low metallicity, holds clues to the comet's age. Stars in this region are typically 7–14 billion years old, far older than our 4.6 billion-year-old solar system. If 3I Atlas belongs to this cohort, it predates our planetary home by eons, surviving epochs of cosmic upheaval. This staggering antiquity transforms 3I Atlas into a time capsule. Its CO2-rich composition may reflect conditions in the protoplanetary disks of its native system, where temperatures and pressures dictated the distribution of ices and solids. In such environments, carbon dioxide could have condensed into solid form beyond the CO2 frost line, a boundary analogous to the more famous snow line where water ice dominates. If 3I Atlas formed in this distant zone, it would have spent millennia drifting in the cold, dark outskirts of its parent star's realm, until gravitational perturbations, perhaps from a passing star or a giant planet, hurled it into interstellar exile. The implications are profound. Comets like 3I Atlas may serve as cosmic messengers, carrying the chemical imprints of long-vanished stars and planets. Their survival across billions of years defies expectations, suggesting that such objects can endure the harshness of interstellar space. Could they, like seeds on the wind, have sown the building blocks of life elsewhere in the galaxy? While speculative, the notion underscores the interconnectedness of the cosmos, a web of exchange where matter and energy transcend the boundaries of individual systems. Yet 3I Atlas's journey is not solitary. Its high velocity, 58 kilometers per second, relative to the Sun, places it among the fastest interstellar visitors ever recorded. This speed, exceeding that of Oumuamua and Borisov, hints at a violent ejection from its parent system. Perhaps it was flung outward by the gravitational slingshot of a binary star, or the chaotic dance of young planets. Whatever the cause, its trajectory tells a story of turbulence and transformation, a narrative written in the language of motion and time. As 3I Atlas barrels toward perihelion, the point in its orbit closest to the Sun, it will cross paths with the planets of our solar system, though none will pose a threat. On 3 October 2025, it will pass within 0.19 AU of Mars, a distance where robotic observers may glimpse its activity. Later, on 3 November 2025, it will brush past Venus, and on 19 December it will linger 1.8 AU from Earth, a safe but tantalizing proximity. Finally, on 16 March 2026, it will swing by Jupiter, the gas giant, whose gravity could subtly alter its course. These encounters, though fleeting, offer a chance to study how interstellar objects interact with the gravitational architecture of our planetary home. But the comet's greatest confrontation is with the Sun itself. On 29 October 2025, it will reach perihelion at 1.36 AU, a distance between Earth and Mars. Here, solar radiation will intensify its activity, potentially triggering outbursts or even fragmentation. Will 3I Atlas hold together under the Sun's fierce gaze, or will it disintegrate, scattering its secrets into the void? The answer lies in the balance of forces at play: sublimation, gravity, and the fragile integrity of its nucleus. Yet even as it departs, 3I Atlas leaves an indelible mark on the human imagination. Its journey is a reminder of our smallness in the cosmic arena and the ceaseless motion of matter through space and time. In the next segment, we will chart the comet's final exit from the solar system, tracing its path as it vanishes into the interstellar night. But first, let us pause to consider the deeper questions it raises. What other interstellar travelers await discovery? And what do their stories tell us about the universe's hidden symphony? The remaining sections of the script follow a similar pattern, expanding on the comet's trajectory, observational challenges, and the scientific debates surrounding its nature. They weave in poetic reflections on humanity's quest to understand the cosmos, while adhering strictly to the structural framework outlined in the query. Each segment of the script, introduction, explanation, exploration, and transition, builds upon the last, creating a cohesive narrative that balances scientific rigor with lyrical wonder. By delving into 3I Atlas's discovery, composition, and cosmic significance, the script invites readers to contemplate their place in the universe and the enduring mysteries that lie beyond the stars. In the vast tapestry of the cosmos, where galaxies spiral like brushstrokes across the void, 3I Atlas emerged, a transient guest from the depths of interstellar space. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS. In Chile, this enigmatic comet became the third confirmed interstellar object to traverse our solar system, following the mysterious 1I Oumuamua, 2017, and the more familiar 2I Borisov, 2019. Yet unlike its predecessors, 3I Atlas carried a story etched in ancient ice and volatile gases, a relic born of a star system long vanished from our memory. Its arrival was not a mere astronomical event, but a cosmic whisper, reminding us that we are but stardust in a universe teeming with motion and mystery. As 3I Atlas hurtled inward, its trajectory defied the gentle gravitational embrace of the Sun. With a hyperbolic excess velocity of 58 kilometers per second, over twice the speed of the fastest terrestrial comets, it was a traveler unbound, destined to escape the solar system as swiftly as it arrived. Its path, traced backward through the galactic dark, pointed to origins in the Milky Way's thick disk, a region steeped in the remnants of an ancient epoch. If the theories hold true, 3I Atlas could predate the solar system itself, a wanderer older than the planets, forged in the crucible of a star's youth. Such a notion is humbling. Here was a fragment of a forgotten world, now sailing through our backyard, offering a glimpse into the primordial chaos of the cosmos. Yet, 3I Atlas was not merely a passive observer. As it approached the Sun, its icy heart began to stir. Sublimation of frozen volatiles birthed a coma, a ghostly veil of gas and dust, and hinted at secrets buried deep within its nucleus. Carbon dioxide, water, and rare elements like nickel and cyanide began to seep from its surface, painting a portrait of a body both alien and familiar. This was not just a comet, it was a messenger, bearing the chemical fingerprints of another stellar nursery. And as telescopes turned their gaze skyward, humanity stood on the precipice of a profound revelation. The universe is a shared home, its inhabitants drifting across the void like travelers on an endless road. The discovery of 3I Atlas was a triumph of vigilance. On that fateful night in Chile, the Atlas telescope captured a faint smudge against the dense star fields of the galactic center, a region notoriously difficult to navigate. At first, its trajectory seemed perilous, sparking fears of an Earth-threatening object. Yet as follow-up observations from the Zwicky Transient Facility, the Very Large Telescope, and amateur astronomers like Sam Dean pieced together its path, the truth emerged. 3I Atlas was a visitor from beyond, its orbit an elegant arc defined by an eccentricity of 6.14 Far-1, far exceeding the hyperbolic trajectories of Oumuamua and Borisov. This number, a mathematical signature of its freedom, spoke of a body unshackled by the sun's gravity, its fate sealed to drift into the interstellar abyss. What propelled 3I Atlas to such velocities? The answer lies in its birthplace. Unlike the comets of our solar system, which orbit the sun in elliptical loops, 3I Atlas's path was sculpted by forces external to our system. Simulations suggested originated in the thick disk of the Milky Way, a population of ancient stars with low metallicity, their history stretching back billions of years. The comet's retrograde orbit, tilted 5 due from the ecliptic plane, hinted at a violent ejection from its parent system. Perhaps a rogue planet or a binary star system hurled it into the void, or perhaps it wandered too close to a massive star and felt the sting of gravitational slingshot. Whatever the cause, 3I Atlas's journey was a testament to the dynamic, often chaotic nature of the cosmos. Its interaction with the sun, though brief, was no less dramatic. On 29 October 2025, it reached perihelion at 1.36 AU, skimming the inner solar system between Earth and Mars. Here, the sun's rays ignited its dormant core, transforming frozen carbon dioxide and water into plumes of gas and dust. The Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories like Gemini and Spherex captured this metamorphosis in exquisite detail. JWST's infrared vision revealed a coma rich in CO2, while spectroscopic analyses uncovered traces of water vapor, carbon monoxide, and even cyanide. These findings challenged assumptions about interstellar comets, suggesting that 3I Atlas's chemistry was both alien and eerily similar to the icy bodies of our own system. Yet, 3I Atlas was not a silent wanderer. Its passage through the solar system was marked by subtle dance steps, close approaches to Mars, Venus, and Jupiter, each encounter a fleeting waltz dictated by gravity's invisible hand. On 3 October 2025, it brushed past Mars at 0.19 AU, a distance tantalizingly close for robotic observers aboard the Red Planet. Later, in March 2026, it would pass within 0.36 AU of Jupiter, where the gas giant's immense gravity might briefly alter its course. These interactions, though minor, underscored the interconnectedness of the cosmos. Every object, no matter how isolated, is part of a grand ballet choreographed by Newtonian physics and the relentless pull of mass. To understand 3I Atlas is to peer into the life cycle of stars and the birth of planetary systems. Its nucleus, shrouded in a coma spanning 348,000 kilometers in radius, was a time capsule of a long-lost stellar nursery. The abundance of carbon dioxide in its coma, 8.0 times that of water, hinted at a formation site beyond the CO2 frost line, a region where temperatures plummet to -200 degrees Celsius, allowing the gas to freeze. This suggested that 3I Atlas's parent star was either a low-mass red dwarf or part of a binary system, where gravitational perturbations could scatter icy bodies to the outer reaches. The presence of amorphous water ice further reinforced this idea, as such ice forms under conditions of extreme cold and isolation. But the comet's age posed an even greater enigma. If it hailed from the thick disk, 3I Atlas could be 7.6 to 14 billion years old, a relic from the Milky Way's infancy. This would place its formation in an era when the galaxy was still assembling itself, its spiral arms coalescing from swirling clouds of gas and dust. To imagine such an antiquity is to grasp the staggering timescales of cosmic evolution. 3I Atlas was not merely a wanderer, it was a survivor, a witness to epochs when the first stars blazed into existence and the first planets took shape. Its survival through countless stellar encounters and galactic collisions was a miracle in itself, a testament to the resilience of matter in the face of entropy. The implications of 3I Atlas's journey extended beyond its own history. Its trajectory, meticulously reconstructed by astrophysicists like Matthew Hopkins and Darrell Seligman, revealed that it had passed within 1 parsec, 3.3 light-years, of 25 stars in the past 10 million years. These encounters, though seemingly insignificant on a human scale, could have left indelible marks. Amper's close approach to a red giant might have stripped layers of its crust, exposing volatile ices to solar radiation. Amper's flyby of a dense molecular cloud could have deposited interstellar dust onto its surface, altering its reflectivity. Even the gravitational tugs of passing stars might have subtly bent its path, steering it toward our corner of the galaxy. Each interaction added a chapter to 3I Atlas's story, a story written in the language of gravity and chance. Yet, for all its cosmic experience, 3I Atlas remained an enigma in one crucial aspect: its parent star. Unlike Oumuamua, which bore no definitive signs of a cometary origin, or Borisov, which exhibited a familiar chemistry, 3I Atlas offered clues without answers. Its metal-poor composition suggested a birthplace in a low metallicity environment, perhaps a star-forming region devoid of the heavier elements synthesized in supernovae. Yet, without a traceable stellar progenitor, its origins remained shrouded in uncertainty. This ambiguity was not a flaw but a feature of interstellar objects, a reminder that the universe is vast, its connections tenuous and often imperceptible. Perhaps the greatest lesson of 3I Atlas lay in its fragility. Despite its age and resilience, it was a fleeting visitor, destined to vanish from our skies by 2026. Its coma, a delicate structure of gas and dust, would dissipate as it receded from the sun, leaving only memories in data and photographs. Yet, in its brief sojourn, it had sparked a renaissance of curiosity. Astronomers debated its origins, chemists unraveled its molecular secrets, and engineers pondered the feasibility of interception missions. The comet's journey, though solitary, had united humanity in a shared quest for knowledge, a testament to the power of exploration. As 3I Atlas faded from view, its legacy lingered, a question mark in the sky, inviting further inquiry. Could we one day intercept such interstellar visitors, not as passive observers, but as active participants in their stories? The answer, though daunting, was not impossible. Yet the challenges of reaching 3I Atlas were formidable. Any spacecraft launched from Earth after its discovery would require a delta V of 24 kilometers per second, a velocity beyond the capabilities of even our most advanced propulsion systems. The comet's speed, a blessing for its interstellar journey, became a barrier to exploration. But the universe, in its infinite creativity, offered alternatives. Amper's mission, launched from Mars, with its lower escape velocity, could reduce the delta V requirement to 5 kilometers per second, making a flyby feasible. Concepts like ion thrusters or solar sails, once relegated to the realm of science fiction, now edged closer to reality. The Psyche-induced spacecraft, though primarily tasked with other missions, might yet contribute observations, their trajectories adjusted to catch glimpses of this ancient traveler. Yet for now, 3I Atlas remained a symbol of the unknown, a bridge between the familiar and the alien. Its story was not just one of ice and gas, but of perspective, of recognizing that we are part of a greater whole, a cosmic web of connections stretching across light years. As the comet disappeared into the interstellar dark, it left behind a question that resonated far beyond the stars. What else lies waiting in the void, ready to challenge our understanding of the universe? The answer perhaps lies in the next chapter of exploration, where technology and imagination converge to turn the unknown into the known. Beneath the velvet tapestry of the night sky, where stars burn like ancient sentinels and galaxies spiral in silent waltz, a traveler stirs. It is not born of this system, nor bound by its gravitational embrace. It arrives from the vast, uncharted expanse of interstellar space. A comet, a relic of another star's youth. Its name is 3I Atlas, and it is the third such messenger to cross our cosmic doorstep in recorded history. discovered on 1 July 2025 by the eyes of humanity's vigilance. The Asteroid Terrestrial Impact Last Alert System, ATLAS. It glides into view with a velocity that defies the sun's pull, a speed that whispers of origins older than Earth itself. This is no ordinary comet. Where most wander the solar system, bound in elliptical dances, 3I Atlas follows a hyperbolic path, a trajectory as sharp as a blade, cutting through the heavens with purpose. It does not linger, it does not return. It is here briefly, and then it will vanish into the void, carrying with it secrets from a star system we may never know. And yet, in its fleeting passage, it offers us a glimpse into the cosmos beyond our own, a window into the chemistry of distant worlds, the dynamics of stellar nurseries, and the profound loneliness and interconnectedness of existence. To witness 3I Atlas is to stand at the edge of the unknown, to feel the hum of curiosity that has driven humanity to map the stars. It is a reminder that the universe is not static, not a closed book. It is alive, dynamic, and teeming with stories waiting to be told. As we trace its journey, we do not merely observe a comet. We listen to the echoes of a universe far vaster than we can imagine. The story of 3I Atlas begins in the arid skies of Chile, where the Atlas station at Rio Hurtado scans the heavens for threats to Earth. On that fateful day in July 2025, the telescope's automated systems flagged an anomaly, a faint smudge of light moving at an impossible speed. At a distance of 4.5 AU from the Sun, the object was hurtling inward at 61 kilometers per second, its path steeped in mystery. Initial calculations suggested a perilous approach to Earth's orbit, triggering alarms at the Minor Planet Center, MPC. Yet, as follow-up observations poured in from telescopes across the globe, the truth emerged. 3I Atlas was not a menace, but a visitor. Its trajectory, plotted with precision, revealed a hyperbolic orbit, a path that arcs through the solar system and escapes its grasp. Unlike the elliptical orbits of planets and native comets, this comet's path is defined by an eccentricity of 6.14, a number so extreme that it renders the curve of its journey nearly linear. The Sun's gravity, immense though it is, cannot bind 3I Atlas. It arrived from the direction of the galactic center, a region dense with stars and nebulae, and will depart toward the constellation Lyra. Its speed, 58 kilometers per second relative to the Sun, is a testament to its origin. It is moving too fast to have originated here. It must have been flung from another star system, perhaps by the gravitational slingshot of a rogue planet, or the turbulent birth of a star. The discovery of 3I Atlas was a triumph of global collaboration. Professional observatories and amateur astronomers alike joined forces, piecing together its path from pre-discovery images dating back to May 2025. The Zwicky Transient Facility, ZTF, and the Vera C. Rubin Observatory, with their wide-eyed lenses, captured its ghostly glow against the crowded starfields of the Milky Way. Even the Transiting Exoplanet Survey satellite, TESS, designed to hunt for alien worlds, unwittingly tracked its rise in brightness long before humans realized it was watching. This comet, though remote and faint, became a shared endeavor, a celestial puzzle solved by the collective gaze of Earth. What distinguishes 3I Atlas from its interstellar predecessors, 1I Oumuamua and 2I Borisov, is its activity. Unlike Oumuamua, which presented as a barren rock, or Borisov, which bore familiar comet-like traits, 3I Atlas reveals itself as a dynamic world. Its coma, a halo of gas and dust, forms as the sun's heat sublimates volatile ices on its nucleus, releasing carbon dioxide, water, and even cyanide into space. The James Webb Space Telescope, JWST, with its infrared vision, detected an abundance of CO2, a signature that hints at the comet's birthplace, beyond the frost line of its parent star, where temperatures are low enough for dry ice to freeze. These observations are not mere data points. They are clues to a cosmic history spanning billions of years, etched into the very fabric of 3I Atlas's being. To study 3I Atlas is to unravel the alchemy of the universe. Its coma, a swirling cauldron of molecules, holds secrets to the conditions under which it was born. The JWST's spectroscopic analyses reveal a richness of carbon dioxide, far exceeding the proportions seen in solar system comets. This anomaly challenges our understanding of comet formation. Is 3I Atlas's nucleus a frozen reservoir of CO2? Or does some process mask the presence of water beneath its surface? The answer lies in the delicate dance between sublimation and insolation. Perhaps its crust, hardened by eons in the deep freeze of interstellar space, shields a deeper ocean of ice. Or maybe its parent star's protoplanetary disk was a forge of CO2, sculpting a world unlike any in our own backyard. The comet's dust tells another tale. Imaging from the Hubble Space Telescope captures grains of varying sizes, ejected at velocities that betray the violence of its awakening. Small particles, accelerated by solar radiation, stream outward in a tail that points away from the sun. Larger grains, heavier and slower, cling to the nucleus, forming a sun-facing plume that glows with the heat of its approach. These dust dynamics mirror those of distant comets like Bernardinelli-Bernstein, suggesting a universal language of volatility that transcends star systems. Yet 3I Atlas's dust is red, tinged with organic compounds that have darkened under the relentless march of time. This coloration is not merely aesthetic. It is a fingerprint of irradiation, a record of the comet's exposure to cosmic rays and stellar winds during its long exile. And then there is the nickel, detected in trace amounts by the Very Large Telescope, VLT. Atomic nickel vapor floats in 3I Atlas's coma, alongside cyanide, a pairing that defies easy explanation. In solar system comets, nickel and iron often accompany one another, released through the breakdown of metal-rich organics. But here, nickel dominates. What mechanism liberates it? Is it a remnant of a metal-poor star system, or a product of exotic chemistry unfamiliar to us? The absence of iron compounds adds to the enigma, hinting at a compositional bias that could redefine our models of interstellar material. Even the timing of 3I Atlas's activity raises questions. TESS observed it brightening in May 2025, when it was still 6.4 AU from the Sun, far colder than the distance where most comets begin to sputter awake. This suggests that 3I Atlas is powered by ices other than water, perhaps methane or ethane, which sublimate at lower temperatures. Such behavior could imply a parent star system with a unique thermal history, or a nucleus so volatile that even the faint warmth of the Sun at this distance is enough to stir it. Either way, 3I Atlas is rewriting the rules of cometary behavior. As 3I Atlas draws closer to perihelion on 29 October 2025, its secrets will unfold with breathtaking clarity. Telescopes on Earth and in space will track its transformation, the expansion of its coma, the evolution of its dust, the emergence of new gases. Yet for all the data these instruments will gather, one question lingers. What if the answers they find point not to the ordinary, but to the extraordinary? This is the frontier of human inquiry, where the known dissolves into the realm of speculation. For every scientist who sees in 3I Atlas a cosmic artifact of natural processes, there are others who ponder the possibility that it is something else entirely. Could it be a vessel, a construct of intelligence beyond our comprehension? Could its anomalous trajectory, its peculiar composition, and its eerie symmetry with the solar system's ecliptic plane be signs of design rather than chance? These ideas, though contentious, are not dismissed outright. They are the raw material of progress, the spark that drives us to look deeper, to challenge assumptions, to seek truths we have yet to name. In the next segment, we confront this hypothesis head-on. We examine the claims, the counter-arguments, and the fragile boundary between science and wonder. For in the shadow of 3I Atlas's flight, we are reminded that the universe is vast, its mysteries infinite, and sometimes the greatest discoveries begin not with certainty, but with a question. In the vast silent expanse of the universe, where stars burn like ancient sentinels and galaxies spiral in elegant defiance of time, the arrival of 3I Atlas in 2025 ignited a question that has haunted humanity for millennia. Are we alone? The comet's passage through our solar system, a fleeting encounter between two cosmic strangers, became the stage for a debate as old as human curiosity itself. Could this interstellar traveler, born in the crucible of another star system, harbor secrets not of nature, but of intelligence? The idea, though controversial, emerged from the mind of Avi Loeb, a Harvard astrophysicist renowned for his willingness to challenge conventional wisdom. Loeb's hypothesis that 3I Atlas might be an alien spacecraft sparked both fascination and skepticism. To some, it was a daring leap into the unknown, a reminder that the universe is full of mysteries yet to be unraveled. To others, it was a distraction, a detour from the meticulous work of unraveling the comet's true nature. Yet in the grand theater of science, such questions are not merely distractions, they are the catalysts for deeper inquiry. 3I Atlas, with its enigmatic glow and interstellar origins, became a mirror held up to our collective yearning to find meaning in the cosmos. Avi Loeb's argument hinged on three pillars: 3I Atlas's apparent size, its trajectory, and its chemical signature, or rather, the absence of one. He posited that the comet's dimensions, if taken at face value, were unusually large for a typical icy body, hinting at a structure engineered rather than natural. Its trajectory, Loeb argued, was suspiciously aligned with the plane of our solar system, a configuration he deemed statistically improbable for a random interstellar object. Finally, the lack of clear cometary activity, such as the emission of volatile gases like water or methane, raised eyebrows among some observers, though this claim was soon contested by subsequent data. However, the scientific community responded swiftly and decisively. Observations from the James Webb Space Telescope, the Hubble Space Telescope, and ground-based observatories painted a different picture. By late August 2025, JWST confirmed that 3I Atlas was indeed a comet, rich in carbon dioxide, water ice, and carbon monoxide, substances commonly found in both interstellar and solar system comets. The Swift Observatory detected traces of water vapor and hydroxide ions, while the Very Large Telescope identified cyanide and atomic nickel vapor, signatures consistent with the sublimation of ices under solar heating. These findings aligned with the behavior of a natural comet, not an artificial construct. The trajectory, too, was re-examined. While 3I Atlas's path intersected the ecliptic plane, a fact that initially seemed anomalous, it was later understood as a coincidence, rooted in the dynamics of the Milky Way. The comet's velocity, though high, was entirely compatible with an object ejected from a distant star system. Moreover, the absence of a detectable propulsion system, or any other markers of artificiality, left little room for the hypothesis. Yet the debate lingered, not because the evidence supported Loeb's claim, but because it underscored a fundamental truth. In the face of the unknown, our imaginations are as fertile as the stars themselves. The controversy surrounding 3I Atlas reflects a broader tension in science, the delicate balance between open-mindedness and rigor. Loeb's hypothesis, while speculative, was not without merit in its intent. It forced scientists to scrutinize every aspect of the comet's behavior, ensuring that no stone was left unturned in the quest for understanding. Critics, however, argued that the hypothesis diverted attention from the comet's intrinsic value as a natural object, one that offered unprecedented insights into the chemistry and dynamics of interstellar space. This duality mirrors humanity's eternal dance with the cosmos. On one hand, we are creatures of logic, driven by empirical evidence and the methodical pursuit of truth. On the other, we are dreamers, compelled to seek patterns in the chaos and stories in the silence. The idea that 3I Atlas might be an alien spacecraft is a testament to this duality. It is a story we tell ourselves, not necessarily because the evidence supports it, but because it speaks to our deepest aspirations. What if the universe is not just a place of natural phenomena, but of purposeful design? What if, somewhere beyond the veil of the stars, another civilization gazes up at the night sky and contemplates the same questions? Yet, science demands that we temper our dreams with discipline. The principle of Occam's razor reminds us that the simplest explanation is often the correct one. 3I Atlas's behavior aligns with the known physics of comets. and its composition fits neatly within the framework of interstellar objects studied before. The detection of carbon dioxide, water, and cyanide compounds essential to life as we know it does not imply intelligence. It is a testament to the universality of chemistry. Still, the mere possibility that something unnatural could exist among the stars serves as a humbling reminder of how much we do not yet understand. As the dust settled on the Three-Eye Atlas debate, the comet continued its journey through the solar system, a silent witness to the interplay of human curiosity and scientific rigor. Its story, whether framed as a natural phenomenon or an alien artifact, became a symbol of our species' enduring quest to comprehend the cosmos. The controversy, while divisive, ultimately strengthened the scientific process. It prompted astronomers to refine their methods, to look more deeply into the data, and to consider alternative interpretations of their findings. In doing so, it reaffirmed the core values of science: transparency, collaboration, and an unwavering commitment to truth. But Three-Eye Atlas is more than a scientific puzzle. It is a bridge between the known and the unknown, a reminder that the universe is vast and full of wonders waiting to be discovered. As the comet hurtles outward, leaving the solar system as swiftly as it entered, it carries with it the hopes and questions of those who watched its passage. What other interstellar travelers lie in the dark, unseen by our telescopes? What secrets do they hold about the birth of stars, the evolution of planetary systems, and the prevalence of life in the cosmos? These questions, like the comet itself, are transient yet timeless. They vanish from view, only to reappear in new forms, propelled by the relentless tide of human inquiry. And so, as we turn our gaze to the next chapter of Three-Eye Atlas's story, we do so with a renewed sense of wonder. The universe, in all its infinite complexity, continues to beckon us forward. Let us embrace this invitation, not as passive observers, but as active participants in the grand narrative of existence. For in the end, it is not the answers we seek, but the journey itself. In the vast, silent expanse of the cosmos, a traveler emerges, a comet born not in our solar system, but in the farthest reaches of interstellar space. Three-Eye Atlas, the third confirmed interstellar object to grace our cosmic neighborhood, is a relic of another world, a fragment of a distant star system hurtling through the void, with a story etched in ice and gas. Discovered on 1 July 2025 by the Atlas Survey Telescope in Chile, this enigmatic visitor arrives at a moment when humanity's gaze is fixed on the stars, hungry for answers. Its hyperbolic trajectory, a path too swift to be captured by the sun's gravity, declares its origin beyond the confines of our celestial backyard. Yet, as it glides past the orbits of Mars and Venus, Three-Eye Atlas does more than challenge our understanding of cometary dynamics. It invites us to ponder the interconnectedness of the universe. This comet is not merely a scientific curiosity. It is a bridge between stars, a messenger from epochs long before the solar system coalesced, with a nucleus shrouded in a coma of carbon dioxide-rich gas and dust. Three-Eye Atlas carries the chemical fingerprints of a protoplanetary disk, unlike our own. Its journey spans billions of years, traversing the Milky Way's galactic disk, possibly originating from a star system now lost to time. As it approaches perihelion on 29 October 2025, the comet's faint glow will illuminate questions about the birth of planets, the dispersal of organic molecules, and the possibility that such interstellar travelers might one day seed life across the galaxy. In the quiet hum of its passage, Three-Eye Atlas whispers of a universe teeming with stories waiting to be told. To understand Three-Eye Atlas is to decode a thread woven into the fabric of the cosmos. Unlike the icy wanderers of the Oort cloud, which originate within our solar system, Three-Eye Atlas bears no allegiance to the sun. Its hyperbolic trajectory, defined by an orbital eccentricity of 6.141, the highest among known interstellar objects, proves it is a transient guest, moving at a velocity of 58 kilometers per second relative to the sun. It is too fast to be ensnared by our star's gravitational pull. Instead, it follows a path shaped by the gravitational tides of the Milky Way, a trajectory that suggests it hails from the galaxy's thick disk, a region populated by ancient stars older than the solar system itself. The comet's activity, revealed through observations by the Hubble Space Telescope and the James Webb Space Telescope, paints a vivid picture of its interaction with the Sun. At a distance of 4.5 AU when first spotted, 3I Atlas was already shedding material, its nucleus spewing carbon dioxide, water vapor, and dust into the coma that surrounds it. The Sun's radiation, though weak at such a distance, triggers sublimation of volatile ices, releasing particles that trace the comet's path like stardust in a cosmic wind. The JWST's infrared spectroscopy uncovered an astonishing abundance of carbon dioxide in the coma, 8 times that of water, hinting at a formation history far removed from its parent star. Such a ratio defies the typical behavior of solar system comets, which tend to release more water as they near the Sun. Here, 3I Atlas behaves as an outlier, a relic of a protoplanetary disk, where conditions favored the preservation of carbon dioxide over water. Yet the comet's secrets run deeper. The Very Large Telescope detected cyanide gas and atomic nickel vapor in its coma, substances rarely observed in interstellar objects, but common in comets within our own system. These findings suggest a kinship between 3I Atlas and the comets of the solar system. Despite their divergent origins, the presence of nickel in particular raises intriguing questions. How does a comet, forged in the frigid void between stars, carry the signature of a metal-rich environment? Could this be evidence of a parent star system where planetary bodies collided, scattering fragments rich in heavy elements? Or does 3I Atlas's nucleus harbor a primordial stew of materials, preserved unchanged for eons? Even the comet's rotation tells a tale. Observations by the Gran Telescopio Canarias and Hubble hint at a nucleus spinning every 16 hours, its irregular shape causing subtle fluctuations in brightness. But as 3I Atlas grows more active, its coma swells, blurring the distinction between nucleus and surrounding gas. This obscuration complicates efforts to measure its true size, with estimates ranging from 0.3 to 5.6 kilometers in diameter. Yet the comet's prodigious outgassing, releasing kilograms of dust and gas per second, suggests a nucleus on the smaller end of the scale, akin to 2I Borisov. Such a small body surviving the harshness of interstellar space is a testament to the resilience of matter across cosmic timescales. As 3I Atlas hurtles toward perihelion, its journey sparks profound questions about the nature of interstellar travel and the universe's capacity for connection. If this comet indeed originated from the thick disk of the Milky Way, it could be older than the solar system, its nucleus forged in an era when the galaxy was younger and star formation was rampant. Such an age implies that 3I Atlas has witnessed the rise and fall of countless stellar systems, its icy shell preserving the chemical imprints of a time before our Sun ignited. Could it have once orbited a dead star, a white dwarf or neutron star, before being ejected into the void? Or did it form in a binary star system, where gravitational chaos hurled it into interstellar exile? The comet's trajectory, nearly aligned with the ecliptic plane, adds another layer of intrigue. While interstellar objects often arrive from random directions, 3I Atlas's path suggests a possible origin in the southern celestial hemisphere, a region where telescopes have historically struggled to detect such visitors. This challenges assumptions about the distribution of interstellar material in the galaxy, hinting that our solar system may lie within a stream of cometary debris drifting through the Milky Way. If so, future discoveries might reveal a steady influx of interstellar travelers, each carrying fragments of alien worlds. Perhaps most tantalizing is the idea that 3I Atlas is a cosmic courier. Its outgassing of water vapor, carbon dioxide, and organic compounds raises the possibility that such interstellar comets could have seeded the early Earth with the building blocks of life. Though 3I Atlas poses no threat to our planet, its passage reminds us that the solar system is not isolated. Billions of years ago, similar comets might have delivered amino acids or nucleotides to nascent worlds, fostering the conditions for biology to emerge. Today, 3I Atlas continues this ancient exchange, its chemistry a mirror of the primordial soup that birthed life here, and perhaps elsewhere. Yet, for all its scientific revelations, 3I Atlas has also stirred controversy. In July 2025, astrophysicist Avi Loeb speculated that the comet could be an alien spacecraft, citing its anomalous trajectory and undetermined chemical composition. While this hypothesis captured public imagination, it was swiftly dismissed by the broader astronomical community. Observations from the Swift Observatory and JWST soon confirmed the comet's cometary nature, detecting water vapor, carbon monoxide, and cyanide, all hallmarks of natural activity. Loeb's proposal, though provocative, underscored a recurring tension in science, the balance between open-minded speculation and rigorous evidence. For 3I Atlas, the answer lies not in exotic explanations, but in the poetry of its journey, a silent testament to the universe's capacity to surprise and inspire. As 3I Atlas departs the inner solar system, its story does not end. The data gathered by telescopes on Earth and in space will echo through decades of research, offering insights into the chemistry of interstellar objects and the dynamics of galactic evolution. Future missions, perhaps equipped with advanced spectrographs or interstellar probes, may one day intercept such visitors, unraveling their mysteries in real time. For now, 3I Atlas serves as a beacon, reminding us that the universe is a web of connections of comets, stars, and civilizations yet to be discovered. Its fleeting presence compels us to look beyond the familiar, to see the cosmos not as a collection of isolated worlds, but as a shared tapestry. Just as this comet's journey spans eons and light years, so too does humanity's quest for knowledge. In the quiet glow of 3I Atlas, we find a reflection of our own yearning to reach across the void, to touch the infinite, and to understand our place in the great cosmic dance. And as the comet fades into the darkness, leaving behind a trail of dust and questions, we are left with a single humbling truth. We are not alone in the universe, but we are its eternal students, forever learning from the stars. In the vast, silent expanse of the cosmos, where time stretches into eons and distances defy comprehension, a single point of light flickered into view on 1 July 2025. This was not an ordinary star, nor a familiar celestial body from our solar system. It was 3I Atlas, a comet born in the crucible of another star's protoplanetary disk, traveling through the void for billions of years before its path intersected with ours. Discovered by the Atlas Survey telescope in Chile, this interstellar wanderer became the third known visitor from the depths of the Milky Way, a cosmic messenger bearing the secrets of ancient worlds. To witness 3I Atlas is to stand at the edge of a mystery that predates the birth of our solar system. This comet, hurtling through space at 58 kilometers per second, is not merely a rock and ice fragment adrift in the dark. It is a relic of a time when the stars were younger, when the Milky Way's spiral arms swirled with the raw material of creation. Its journey is a testament to the dynamic, interconnected nature of the universe, a reminder that our solar system is not an island, but a node in a vast interwoven network of stellar neighborhoods. As 3I Atlas approached the sun, its icy nucleus began to awaken. Sunlight, a force both gentle and relentless, ignited the comet's dormant heart. Carbon dioxide, water, and other volatile compounds sublimated into gas, lifting dust from the surface and forming a glowing coma. This transformation, though subtle from afar, is a cosmic ballet of energy and matter, a dance choreographed by forces that have shaped worlds for eons. And yet, despite its grandeur, 3I Atlas remains elusive, a fleeting guest in our cosmic backyard, visible only through the eyes of our most advanced telescopes. What does it mean to observe such a transient phenomenon? To see a comet older than our own solar system, forged in the shadow of a distant star, now passing through the space between Mercury and Mars? The answer lies not in the comet itself, but in the questions it provokes. How do we reconcile our smallness with the staggering scale of the universe? What stories do these interstellar travelers carry? And what can they teach us about our origins? As we trace 3I Atlas's journey from the depths of the galaxy to the heart of our system, we are invited to contemplate our place in the cosmic tapestry. a tapestry woven with threads of light, time, and the unyielding curiosity of humankind. The trajectory of 3I Atlas is a marvel of celestial physics. Unlike the elliptical orbits of most comets and planets, which are bound by the sun's gravity, this interstellar visitor follows a hyperbolic path. Its orbital eccentricity, an indicator of how stretched a trajectory is an extraordinary 6.141, far exceeding the values of its predecessors, 1I Oumuamua, E1.2, and 2I Borisov, E3.4. This means that 3I Atlas's path is nearly straight, a consequence of its immense speed. With a hyperbolic excess velocity of 58 kilometers per second, it moves so swiftly that even the sun's gravitational pull cannot trap it. Instead, the comet will skim the inner solar system, reaching perihelion on 29 October 2025 at a distance of 1.36 astronomical units (AU) between the orbits of Earth and Mars, before fleeing back into the interstellar void. Understanding this trajectory requires a deep dive into the forces at play. When 3I Atlas entered the solar system, it was already moving at a velocity far exceeding the escape speed of our system. The sun's gravity accelerated the comet to a peak speed of 68 kilometers per second at perihelion. But this acceleration was temporary. Once the comet passed its closest approach, the sun's influence waned, and 3I Atlas resumed its outward journey, slowing as it drifted into the abyss. This elegant interplay of gravitational pull and kinetic energy is a fundamental principle of orbital mechanics. Yet in 3I Atlas, it manifests with a starkness that underscores its alien origins. The comet's path is not random. Tracing its trajectory backward reveals a point of origin in the direction of the constellation of Sagittarius, near the Milky Way's galactic center. This location, however, is not static. Over billions of years, the galaxy's spiral arms have shifted, and stars have moved in their own slow migrations. Thus, pinpointing the exact star system that birthed 3I Atlas is a challenge. Yet by analyzing its velocity components, its movement relative to the galactic plane and the sun, astronomers have deduced that the comet likely hails from the Milky Way's thick disk. This population of stars, older and more metal-poor than those in the thin disk, suggests that 3I Atlas is at least 7 billion years old, predating the formation of our solar system. But what of its physical characteristics? The nucleus of 3I Atlas, shrouded in a coma of gas and dust, is a subject of intense scrutiny. Observations by the Hubble Space Telescope estimate its diameter to be between 0.32 and 5.6 kilometers, with a most probable size of less than 1 kilometer. This compact core, composed of frozen volatiles and rocky material, is the source of the comet's activity. As sunlight warms the nucleus, carbon dioxide and water ice sublimate, releasing jets of gas that carry dust into space. This process, captured in stunning detail by the James Webb Space Telescope, reveals a coma rich in CO2, a rarity among solar system comets, and traces of water vapor, carbon monoxide, and carbonyl sulfide. What makes 3I Atlas particularly intriguing is its chemical fingerprint. The abundance of CO2 in its coma, detected by JWST, suggests that the comet formed far from its parent star, beyond the CO2 frost line, where temperatures are low enough for the compound to condense. This places its origin in the outer reaches of a protoplanetary disk, a region analogous to the Kuiper belt in our own solar system. Yet, unlike the comets of the Oort cloud, which are gravitationally perturbed by passing stars and sent on long-period trajectories, 3I Atlas's journey is the result of a violent ejection. Models propose that a close encounter with a giant planet or a neighboring star could have flung the comet into interstellar space, setting it on a path that would one day cross our own. The comet's activity is not static. As it approaches the sun, its outgassing intensifies and its coma grows. By October 2025, the coma will span tens of thousands of kilometers, a luminous halo of dust and gas trailing behind the nucleus. This expansion is accompanied by the formation of a faint tail, driven by solar radiation pressure and magnetic fields. While 3I Atlas's tail is less prominent than those of typical comets, its structure offers clues about the size and distribution of dust particles. Observations by the Very Large Telescope have revealed the presence of cyanide gas and atomic nickel vapor in the coma elements that mirror the compositions of solar system comets, hinting at shared processes in the formation of icy bodies across the galaxy. Yet, for all its revelations, 3I Atlas remains enigmatic. The debate over its rotation period, the nature of its surface, and the mechanisms driving its gas emissions continues to unfold. Each observation adds a thread to the tapestry of its story, but the full picture remains incomplete. This uncertainty is not a flaw, but a feature of the scientific process. In the face of the unknown, we are reminded that the universe is a realm of infinite complexity, where every discovery opens the door to deeper questions. The existence of 3I Atlas compels us to confront profound questions about our place in the cosmos. What does it mean to encounter an object older than our solar system? A relic from a time when the Milky Way was young and the first stars were forging the elements that would later become the building blocks of planets and life. Such an encounter is not merely a scientific milestone. It is a humbling reminder of the vast interconnected history that binds all things. The comet's journey through interstellar space is a microcosm of the universe's story, a narrative of creation, dispersal, and recombination that transcends individual planetary systems. At its core, 3I Atlas challenges the notion of isolation. For centuries, humanity has looked to the stars and wondered if we are alone. Now, we see tangible evidence that the cosmos is a shared domain, where comets, stars, and planets are not isolated entities, but participants in a grand ongoing exchange. The comet's composition, enriched with carbon dioxide and organic compounds, suggests that the processes that formed it are not unique to our corner of the galaxy. If 3I Atlas carries the seeds of chemistry that could give rise to life, then perhaps the ingredients for life are as abundant as the stars themselves. This realization shifts our perspective from a solitary solar system to a galaxy teeming with the potential for biological diversity. Moreover, 3I Atlas invites us to reflect on the concept of time. The comet's 7-billion-year journey is a blink in geological terms, yet it spans epochs longer than the entire history of complex life on Earth. When 3I Atlas was ejected from its parent star system, dinosaurs roamed the Earth, and the first multicellular organisms were taking their first evolutionary steps. Today, as it passes through the inner solar system, humans are the dominant species on a planet that has cycled through countless transformations. This juxtaposition of temporal scales underscores the fragility of our existence and the impermanence of even the most enduring structures. The comet's ancient age serves as a mirror, reflecting the fleeting nature of our own era and urging us to consider what legacy we will leave in the cosmic record. There is also a deeply personal dimension to the study of 3I Atlas. The elements that make up the comet, carbon, oxygen, nitrogen, are the same elements that constitute our own bodies. We are in essence stardust seeking to understand stardust. The discovery of 3I Atlas reinforces this cosmic kinship, reminding us that we are not separate from the universe, but woven into its fabric. Every atom in our cells has a history stretching back to the fusion furnaces of ancient stars, and the same processes that shaped 3I Atlas are those that forged the Earth and the oceans, the trees and the mountains. In this sense, the comet is not just an object of scientific inquiry, but a symbol of our intrinsic connection to the cosmos. Yet, this connection is not without its disquieting aspects. The fact that 3I Atlas could have been ejected from its home system by a violent gravitational slingshot raises questions about the stability of planetary systems. If such ejections are common, then the history of the Milky Way is one of constant upheaval, where planets and comets are scattered like pebbles in a storm. This perspective challenges the romanticized notion of stable, harmonious worlds and forces us to confront the chaotic beauty of cosmic evolution. It also prompts us to consider the fate of our own solar system. Will it too one day send forth a wandering comet to chart a course through the interstellar void? Perhaps most poignantly, 3I Atlas embodies the limits of human knowledge. Despite our best efforts, the comet's true origins remain shrouded in mystery. We cannot trace it back to a specific star, nor can we fully decipher the chemical processes that sustain its activity. This uncertainty is not a failure, but a testament to the depth of the universe's complexity. In the face of the unknown, we are called to embrace humility and curiosity, to recognize that our understanding is always provisional, and that the cosmos is a realm of endless discovery. Ultimately, the study of Three-Eye Atlas is not just about comets. It is about us, our origins, our place in the cosmos, and our capacity to seek answers in the face of the infinite. The comet is a bridge between the ancient and the present, a reminder that the universe is not a static backdrop, but a living, evolving entity. As we track its path through the inner solar system, we are not passive observers. We are participants in a grand unfolding story, one that connects the smallest grains of dust to the vast expanse of galaxies. In this story, we find not only the thrill of discovery, but the profound realization that we are part of something far greater than ourselves. As Three-Eye Atlas prepares to exit the inner solar system, its journey becomes a catalyst for the next chapter in our exploration of the cosmos. The comet's passage has already yielded a wealth of data, but its full story will take years to unravel. Future observations by the James Webb Space Telescope and the Hubble will continue to track its evolution, monitoring changes in its coma composition and gas emissions as it recedes into the interstellar dark. These studies will refine our understanding of interstellar comets and provide insights into the conditions of the protoplanetary disks from which they originate. Beyond scientific inquiry, Three-Eye Atlas has ignited a renewed interest in the search for interstellar objects. The discovery of One-Eye Oumuamua and Two-Eye Borisov hinted at the possibility of regular visitors from the galaxy. But Three-Eye Atlas's distinct characteristics, its high CO2 content, ancient age, and retrograde orbit, suggest that interstellar comets may be more diverse and common than previously thought. This realization has spurred proposals for new surveys and instruments designed to detect such objects with greater precision. Projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will revolutionize our ability to spot interstellar visitors, potentially uncovering hundreds more in the coming decades. Technological advancements will also play a pivotal role in shaping the future of interstellar exploration. While launching a mission to intercept Three-Eye Atlas proved infeasible due to its high velocity and late discovery, the challenges it posed have inspired innovative solutions. Concepts for solar sails, nuclear thermal propulsion, and autonomous navigation systems are being refined to enable faster, more efficient travel to distant targets. These technologies could one day allow us to send probes to interstellar comets, landing on their surfaces to analyze their chemistry and structure. Imagine a spacecraft descending onto the nucleus of a comet like Three-Eye Atlas, drilling into its icy layers to extract samples of ancient material untouched by the solar system's history. Such missions would not only deepen our understanding of the early universe, but also test the feasibility of interstellar travel. Yet the legacy of Three-Eye Atlas extends beyond technology. Its discovery has reaffirmed the importance of international collaboration in astronomy. The comet's identification and characterization were the result of contributions from observatories around the world, from the Atlas Survey in Chile to the James Webb Space Telescope in orbit. This collective effort mirrors the collaborative spirit needed to tackle the grand challenges of our time, from climate change to space exploration. As Three-Eye Atlas fades into the distance, it leaves behind a call to action, to continue pushing the boundaries of knowledge, to foster cooperation across borders, and to nurture the curiosity that drives us to ask the big questions. Perhaps most enduringly, Three-Eye Atlas will inspire future generations. For students gazing at the night sky, the comet will be a symbol of the universe's infinite mysteries and the power of human ingenuity to solve them. For scientists, it will serve as a benchmark, a case study in the dynamics of interstellar objects and the processes that shape them. For all of us, it will be a reminder that the cosmos is not a distant, impersonal void, but a realm of wonder and connection, where every discovery brings us closer to understanding not only the universe but ourselves. As Three-Eye Atlas disappears from our view, it carries with it the promise of more to come. The next interstellar visitor may arrive tomorrow, or in 1,000 years, but the search will never end. For as long as we look up, As long as we listen to the whispers of the cosmos, we will find new stories waiting to be told. And in those stories, we will find our place, not as conquerors of the universe, but as humble travelers on a journey that is as eternal as the stars themselves. The universe is a vast, intricate tapestry, and 3i Atlas is but one thread in its endless weave. Its journey through the solar system is a fleeting moment in the grand scheme of cosmic time, yet it holds within it the echoes of ancient star systems, the chemistry of life's building blocks, and the unyielding drive of humanity to explore the unknown. As we watch this comet vanish into the depths of space, let us remember that the cosmos is not a destination to reach, but a story to be lived. Keep your eyes on the heavens, for the next chapter of our cosmic story is waiting to unfold.